In this video, we will explore Newton's three laws of motion. Before we start discussing Newton's laws, we need to make sure we understand the concept of inertia, which was developed by Galileo many years before Newton. Inertia is the tendency of an object to resist a change in motion. For example, this small mouse here would like to resist a change in motion, but when the large block approaches it, you can see that the mouse does not have a lot of inertia. It gets swept away by the block. Here, even though the mouse is trying to push hard, the block doesn't move. Even with a running start, the mouse is unable to move the block. The block has much more inertia than the mouse did. We can see that the mass of an object is related to inertia. In fact, the mass is a measure of an object's inertia. And because inertia is a resistance to change in motion, mass can be considered to be a measure of an object's resistance to change in motion. Before, we looked at how easy it was to move an object that was at rest with the mouse and the box. But what about stopping an object that's already in motion? You can see that it is quite easy to stop a tennis ball that is coming towards you, but stopping a cannonball is something else entirely different. Once again, causing something that has very little mass to move is not difficult because it has very little inertia, compared to trying to move something that has a lot of mass, which has a lot of inertia. Now we can look at Newton's first law of motion and examine specific parts of it. Notice there are two conditions. One, an object is at rest, and the other one, an object is in motion. For the first condition, it simply says an object at rest will remain at rest. For the second condition, however, it says an object in motion will maintain a constant velocity, and that means two important things here. One, that it will maintain a constant speed, and two, that it will maintain a constant direction in a straight line. The final part of Newton's first law says that these conditions will remain unless acted upon by a net external force. Now let's look at an object that's having a force directed on it. We have a force on the left and on the right of equal magnitude. Because they are both equal and in opposite directions, the net force is zero. That means this object will not move if it is at rest, or if it's in motion, it will continue at the same motion. However, if one of the forces is less than the other, then you have a net force that's positive in one direction, and the object will accelerate in the direction of the greater force, of the total net force. Because of its connections to the concepts of inertia, Newton's first law is often known as the law of inertia. In Newton's second law, the forces on various masses are related to their accelerations. Here we have two masses of the same size with two different forces being acted on them. Now, as you would expect, the larger force causes the mass to accelerate faster. This lets us know that acceleration is directly proportional to force. Now we have two masses of different sizes, each being pushed by the same size force. Once again, it's easy to see that the larger mass will move much more slowly than the smaller mass. From this we can conclude that acceleration is inversely proportional to mass. We can show the relationships between acceleration, force, and mass in this equation. However, the more common form of this equation is F equals ma. With this equation, we can now determine the units for force. Because force is equal to mass times acceleration, and mass is in kilograms, while acceleration is in meters per second squared, the units for force are kilogram meters per second squared. This is quite a mouthful to say, however, and so scientists use the term Newton for the units of force, where 1 Newton is equal to 1 kilogram meter per second squared. You may already be familiar with this statement for Newton's third law of motion, that for every action there's an equal and opposite reaction. But there's more to it than just that. To help us discuss this third law, let's look at this example of a hammer striking a nail. This brings up an important part about Newton's third law, that is that forces always occur in pairs. If you remember from the previous video, we saw that all forces have something that cause the force, the agent, and something that receives the force, or the object. So forces will always occur in these types of action-reaction pairs. Examining the third law, we see that these two forces are equal. That is, the force of the hammer on the nail is of the same magnitude as the force of the nail on the hammer. The second part of the third law states that these forces are opposite. That is, they are in opposite directions to each other. And you can see that the hammer exerts a force downward on the nail, and the nail exerts a force upward on the hammer. As stated in your textbook, Newton's third law of motion points out the action-reaction pairs that are involved with each force. It also states that these action-reaction pairs act on two different objects. For example, the hammer acted on the nail and the nail acted on the hammer. And finally, it mentions that these members of the action-reaction pair act in opposite directions and are equal in magnitude to each other. This concludes this video on Newton's three laws of motion. I just can't wait to get started drawing some free body diagrams. I know you will love them too.